Well, welcome everybody. Good afternoon, good evening in the UK. Thank you. We are having today the pleasure to have with us Amanda Cooper-Sarkar in the Colloquium of the Institute of Physics at UNAM, the largest university of Mexico. And basically what I want to say here is that it's a great pleasure for us to have you here, Amanda Cooper-Sarkar, for accepting giving this colloquium to all of us. We are very eager to learn about the structure of the proton. And I mean, after 85 years of Institute of Physics, this is one of the colloquia in Mexico that has most tradition. And I am completely sure that everything that we are gonna learn today is going to rest with us forever. Thank you very much for being here. Welcome, this is your home, please.
Okay, so let me introduce Mandy. Sorry, I'm in an area with planes. So Professor Cooper-Sarkar did a bachelor degree and PhD at Oxford University in the 70s. Then she held a few postdoc positions, one at the Tata Institute in Bombay, another one at Keck at Japan, then back in Europe, and also Europe, UK, and CERN as well. Then she came back to Oxford, where she has now a full professorship. And she also won a few awards. I see here the Chadwick Medal, which is a really wonderful award. And she's an expert in deep energy scattering. That's why I'm the link with IFUNAM to invite her, actually. And she's really an expert. She's a member of Atlas, and she also is one of the founder member of the PDF4LHC group. And so welcome, Mandy, and thank you so much for giving the colloquium. I think we're gonna ask questions after the colloquium. So people just please write down your questions and wait for the end of the colloquium. Thank you, Mandy.
Okay, so shall I start?
Sure.
Okay, so right, well, it's just been said that this is a colloquium about the deep structure of the proton, and indeed why that matters for the LHC. So what we teach our undergraduates is that there are 3 quarks in a proton, a U, and a D. But it's actually a lie, or let's just say it's an oversimplification, right? There are many, many more quarks in the proton. There are quarks and antiquarks, and there are gluons. These particles are collectively known as partons. The only truth in the idea of 3 quarks in a proton is that if you take the number of quarks minus the number of antiquarks, then that will be 3. There are 3 residual quarks in the proton, which we thus call the valence quarks, because they give the properties to the particles that they're making up, what we call its flavor properties, the various types of quarks. Now, much more interesting than just counting what numbers of quarks are what's in there, much more interesting than that is the distribution of these quarks and gluons in terms of their momentum, the fraction of the total momentum of the proton that each kind of quark, antiquark, or gluon takes. And those are known as the parton distribution functions. Now, the figure that's on the left there is a figure of a measurement and extraction of these momentum distributions. Now, note first of all that the X scale is a log scale. So this is going from the full momentum of the proton at the right-hand side, 1, all the way down to only 10 to the minus 4 of the momentum of the proton. And what you're seeing is how much of that momentum each kind of quark takes. So you've got the big, I'm just wondering, can you see my pointer? I guess you can.
Yes, we can.
Yeah, so you've got the distribution of the U valence quark and the D valence quark, and you can see there that's about 2 for 1, like in the traditional 2 U's and 1 D. But of course, these things don't have to have the same shape just because the overall numbers add to 2 and to 1. And then you can see the shapes of what we call a sea of quark-antiquark pairs, and indeed of the gluons, which are the particles that are effectively sticking those quarks and antiquarks together into the proton. Another thing to note about this figure is that I've actually multiplied down the distribution of the gluon and the C quarks by a factor of 20 in order to put them nicely on the same plot. In actuality, they're 20 times larger. So you can see from that at low momentum fractions, the proton is really all gluon and C. Now, these momentum distributions are predicted by the dynamics of interactions between quark and gluons, which is determined by the field theory of quantum chromodynamics. And I'll go into that a little bit, but before that, let's just say, how is this relevant to the LHC? Well, of course, what we're doing at the LHC is colliding protons, but it's not really the protons that are doing the colliding directly. What's happening is, say, if proton A is coming in and proton B is coming in, then one of the partons, that's those quarks and gluons inside proton A, is taking a fraction, let's call it x1 of the total momentum of that proton. And in the other proton, there's a different kind of quark, maybe taking a total momentum x2 of that proton. And it's those partons that are coming together to make something new. So the actual center of mass energy squared of the collision that's going on is not just whatever we put into the beams, which is normally 13 TeV squared. It's actually x1 times x2 times this 13 TeV squared. So the energy involved in each collision at the LHC is different. And the probability that you'll get collisions depends on the joint probability that proton A contained a parton of momentum fraction x1 and proton B contained a parton of momentum fraction x2. And then that those two partons were of the right type to make whatever final state you want to look at. That's the cross section for forming a final state that we'll just call X in this simple diagram. So you've got the master equation for the cross section of this process here, involving the probabilities of each of those partons having the right center of mass energy and the probability of them coming together to make a certain required final state X. So that's what we're trying to determine, and that's what we're measuring at the LHC. And to measure any cross-section at all, any process coming out, you're going to need to know what these probabilities are that a certain parton had a certain subfraction of the momentum distribution of the proton. Now, how did we come indeed to know anything about the partons in a proton? The fact is, you wouldn't find this out by slinging protons on protons. It's not an efficient way. The way we find it out is by lepton proton interactions. And for example, at the Hera Collider, which was located in Daisy, Hamburg, and it ran from 1992 to 2007 at various energies of the proton, making various center of mass energies of the collision of electron on proton. It ran with a total luminosity of 500 inverse picobarn, split roughly equally between E plus and E minus beams. Now, how does colliding something like an electron with a proton tell you something about the partons in the proton? So here we have a sort of pedagogical slide. Here is what an electron-proton collision looks like from the point of view of an experimentalist. And here's what it looks like from the point of view of a theoretician. So for an experimentalist, we see a proton beam going one way and an electron beam going the other way, colliding here. And outgoing, you will get an electron coming out of the collision, and then a lot of debris from the proton having broken up. And we can measure these things in our detectors. We measure the energies of the we know the energies of the incoming electron and proton. We can measure the energy of the outgoing electron and the scattering angle that it has in the process. We can also measure a lot about these hadrons. Now, if we look instead at the way a theoretician thinks of this, it's a lepton exchanging a virtual boson with a proton and becoming an outgoing lepton and an outgoing final state that again we'll call X. And this is calculable in terms of a leptonic tensor that describes the top vertex and a hadronic tensor that describes the bottom vertex. And you can, construct various 4-vector, these are the momentum exchanges. So K minus K prime is the amount of 4 momentum given to the exchange vector boson, which gives us what we call the scale of the process, meaning how hard are we hitting this proton. Then the momentum of the proton plus that of the electron is the overall center of mass of the process. And you can also construct from these momentum vectors, that all of them given in the diagram, various 4-vector invariants, which we'll call these ones X and Y, and the combination of them, the scale, is actually the overall center of mass energy times X times Y. Sorry for a minute, going too fast. I'm just mentioning those in the hope that you might remember them in a minute, right? Basically, there's a lot of things about this interaction that is measurable. Now, if we're trying to do the calculation of the cross-section of such an interaction, we've got the leptonic part, which is actually really easy. We'll get, there's the inverse propagator of a photon, and here's the fine structure constant. And then there's the hadronic part, where essentially we had to parameterize our ignorance of what was really going on with the hadrons at the beginning of all this. And we parameterize it in terms of various what are called structure functions, F2, FL, and XF3. And I'm sorry, that keeps happening to me. And some of the kinematic variables here, the Y variables, are essentially in terms of the scattering angles. Now, that is in all generality, the form of this is just dictated by Lorentz invariance. But if you want to try and imagine that maybe this whole scattering takes part in what's called the quark parton model, then the picture you have in mind is this, that when the virtual boson is exchanged, it's not hitting just a whole incoherent proton, it's hitting a single quark that comes out of that proton, and a scattered quark is coming out of that. Now, if you think about the kinematics of this, the momentum of the outgoing quark there is x times p, the fractional momentum x of the momentum of the proton coming in, and the virtual momentum q, all squared. So multiply that out and set it equal to 0, because you're going to assume that quarks are massless. Now, the other thing you're going to assume about this is we're at sufficiently high energies that we can also assume that p squared is 0. In other words, that protons are more or less massless, but pretty well always at much higher energies than that. So what this actually tells us, if we get rid of the p squared term, is that q squared plus 2xp dot q is 0, or in other words, that x is q squared over 2p dot q, where, as I said on the slide above, big Q squared is just the negative of little q squared. It so happens that the exchange for momentum is always negative, and hence it's big Q squared, which is the positive quantity. And in this equation, therefore, what we've got is an expression for the fractional momentum of the struck quark in terms of kinematic invariance that we can actually measure. So we can measure that fractional momentum. The other thing we can do, we may not know what these structure functions are, but we can measure them, because in these scatterings, we can measure the cross-section as a function of all the variables in this, in terms of y, the scattering angle, in terms of x, in terms of q squared. Now, the prediction of the quark parton model, which, I mean, this is the subject of a graduate course to work all this out, but the prediction was that the differential cross-section for lepton-proton scattering would actually only depend on one of those structure functions, the one we called F2. What that means is that the angular distributions that we get are consistent only with this y plus 1 minus y squared distribution, and we don't have any of the other distributions. And not only that it would depend only on F2, but that in fact, the quark parton model says that the result would be independent of the scale of the probe, of how hard we're hitting things. It would be a weighted sum of quark and anti-quark multiplied by their momentum fractions and weighted by their fractional charges. That E sub I means either 2/3 for a U-type quark or minus a third for a D-type quark. And that's the quark-parton model prediction. So how good is it? If we look at this plot, that prediction is saying that this structure function F2 should not depend on Q squared. Now look at the scale again. The scale is a log scale going across 5 decades of Q squared. And for a large part of this plot, the different lines are all different momentum fractions of that struct quark that we are measuring. For a large part of this plot, this prediction is actually pretty good. And indeed, if we were not hitting point-like partons, the prediction would actually be that F2 would have to depend on the scale as 1 over Q squared. So on this kind of a plot like this. So the plot is not only telling you the quark partons model's pretty good, it's kind of confirming that the partons are point-like. And we know that down now to 10 to the minus 19 of a meter. On the other hand, it's clearly not perfect. Things are going up a little bit at low x's here. They're going down a little bit at high x's. And in fact, that's because the quark-parton model is too naive. We need quantum chromodynamics to refine it. So what does that mean? Well, it means that in the naive picture that we had of what might be happening, so if I just go back here again, we had just a point-like scatter of the virtual boson off a single quark. Now, what quantum chromodynamics is saying to us is, well, maybe it's not so simple as that. Maybe that quark, before it gets struck by the virtual boson, emits a gluon. Maybe alternatively, it's actually a gluon that's coming up out of the proton and it splits to a Q-Q bar pair, and one of those is what's being hit by the virtual boson. These processes become possible when you consider quantum chromodynamics. And what it means technically is that instead of having our F2 structure function just described by a simple point-like scattering, we have to take into account the cross-section for this process. And if we do that, we find that that gives our F2 structure function a little extra piece, which depends on Q squared. So again, this is the subject of a whole graduate course to go into this in detail, but what you get out is that your F2 structure function is going to depend slightly on Q squared, in fact, through a log of Q squared, right? And that's actually what we were seeing in that plot there, that this is just a gentle log behavior in terms of Q squared that you see at high x and at low x. We also have to consider this process where it was actually a gluon that came out of the proton. And that means that the overall rate at which this extra piece that we're getting is changing with Q squared, we call that evolving with Q squared, has a piece that depends on the original quark density from this diagram and another piece that depends on the gluon density from this diagram. And the two of them together make up how fast the quark densities are changing. They also, by corollary, will make the gluon densities change. Now, what that means is that in leading order QCD, our prediction for the F2 structure function now has a slight dependence on Q squared. It depends on it, as I said, through the log. The theory can predict for us the rate at which those parton distributions are evolving with Q squared, but it won't predict for you what their original shape is at some initial Q squared value. And note, there is a minimum scale below which we do not dare to tread, because another thing about quantum chromodynamics is that its coupling parameter runs, right? It changes with the scale. It's actually quite a strongly coupled at low scale, low Q squared, far less so at high Q squared. The fact that it is a relatively small at high Q squared is exactly why we can calculate in quantum chromodynamics. But we daren't push our luck too low, because we'll be getting into a region where we really can't make perturbation theory work. So there is a lower limit to this. Just as a sort of extra technical detail, is this leading order picture I just looked at enough? Well, no, it isn't. You have to consider many more complicated diagrams than that, going from leading order to next to leading order to next to next to leading order. And those terms just mean how many powers of alpha S that's the strong coupling parameter, do I need to include in my Feynman diagram? And what that will mean for us is the structure function F2 will no longer be so neatly and simply expressed in terms of the protons. We'll have to take the quark and the gluon densities and convolute them with calculated coefficient functions. But the good news is it's all calculable. If you knew what those parton distributions were at some starting scale, you have the answer then from quantum chromodynamics as to what happens to them for all other higher energy scales. And just to sort of put that in terms of the diagram we first started with. So here's the diagram again of the U valence, D valence, the total C and the gluon. In fact, the green is at next to leading order now rather than leading order. And I'm showing now what happens to this if I go from a fairly low scale to quite a high scale, Q squared of 10,000. Now that's roughly the scale at which, say, you can be looking at W and Z bosons, right, which have masses around 80 or 9 GeV. So their energy scale is their mass squared. That kind of scale is what we look at the LHC. And what you find is that because the partons evolve with the scale, that having looked like that, they evolve through all these splittings that are calculable in quantum chromodynamics to look like this. That means that, sorry, I have to go back. Yeah, what that means is that the valence quarks keep just splitting off gluons, right, and losing energy so that they go down, losing their energy, whereas what they're doing is they're splitting into gluons and into QQ bar pairs. And that means that the C and the gluon are rising. So that's why you get at high X, you get things, you know, decreasing, and at low X, you get them increasing. And that we saw, if I dare move back here again, right, at high X, they're increasing with scale. Sorry, at low X, they're increasing with scale, and at high X, they're decreasing with scale. So that's what we were seeing here as a function of X and as a function of scale. So we learn about these things from the Hera collider at relatively low scales, and now we're applying this knowledge at relatively high scales at the Large Hadron Collider, where indeed I said before that at low X, the proton is pretty well all gluon C, and this just becomes increasingly true the higher scale you move to. The harder you hit something, the more you see of all this substructure and all this activity. So, the only thing that we don't know from the theory, right, we know how things evolve with scale. The only thing we don't know from the theory is what are the shapes of the parton distributions at some starting scale. That's a non-perturbative problem that is not yet solved. Indeed, people are trying very hard to solve this from lattice gauge theory, but this is not yet a mature field in terms of the parton distribution. So currently we have to measure this. How do we measure it? Well, I mentioned only electron-proton scattering, and I said that most simply at leading order, they are given in terms of weighted sums of the quarks and antiquarks, where the weight is the fractional charge squared, so 2/3 squared or -1/3 squared for U and D type. Strange and charm are just other examples of D type and U type respectively. But we don't just scatter off protons, we can scatter off isoscalar targets with equal numbers of neutrons and protons. And that means we would average out these quarks between the proton and the neutron on the assumption that a U in the proton is pretty much the same as a D in the neutron and vice versa. Right? Those are the low energy formula for photon exchange. Hera did go beyond that to also W and Z exchanges, but I won't go into that today. I'll mention that also there were other experiments where what you're using as your probe rather than a charged lepton is a neutrino or an antineutrino. And for those processes, you can also calculate what are the quarks involved in the structure function, and you get an even-handed distribution of quark and anti-quark for the F2 structure function with neutrinos. Whereas in neutrinos, because again they are, this keeps happening, because we can have parity violation, you could also have a non-zero XF3 structure function, which is very useful information-wise because it tells you the difference between quarks and anti-quarks, and hence we can actually measure the shape of valence quarks. And then we essentially got the shape of the gluon itself from the theory by looking at how fast the rate of change of all the parton shapes is with Q squared, because that is determined by the gluon term. So all we need to know is what are these parton distributions at the starting scale. We've got various measurements we can make that can tell if, how this works in terms of the different flavors of the quarks. So how do we actually know what to do? Well, the fact is you don't really know it. You have to parameterize it, right? You would take a particular quark of some flavor like UU bar, DD bar, strange, anti-strange, charm, gluon, and so on, and parameterize it with a basic form ax to the b1 minus x to the c times some polynomial. And the polynomials you can use could be ordinary polynomials of x or root x. They could be Chebyshev's, Bernstein polynomials. They could even be a neural net. Typically, at least at the beginning of this field, we had something like 20 or 30 parameters. And then some of these things you can fix through conservation, well, some rules essentially, the conservation of the total amount of momentum, the conservation of the number of quarks of each flavor. There can only ever be, 2 valence quarks and 1 valence U quarks and 1 valence D quark. But there's an awful lot of additional parameters here where you either have to fit them or they're choices that you make. Now, the choices, the model choices you make are, where are you going to start? You have to start at some starting scale. What value of the starting scale, let's call it Q sub 0, will you take? Right? What form of this parameterization will you take? Which data will you use for the fit? You can use, charge lepton on proton, on deuterons, you can use neutrinos. These days we use LHC data. What kind of kinematic cuts are you going to apply to your data to make sure that you're not in the non-perturbative regime? How are you going to deal with the heavy quarks? These are all choices that have been worked out by the PDF fitting community. And I'm saying this now just to emphasize that not all groups which do this job make exactly the same choices. But what we do is we choose the parameterization and then we use quantum chromodynamics to evolve our partons to higher scales. We construct predictions for all the measurable structure functions. Again, those predictions are completely from QCD, right? No unknown things in that. And we then fit something like 3,000 and odd data points to our something like 20 or 30 parameters, doing a chi-squared fit to the data. That's typically what is done. Now, the very fact that so few parameters could allow us to fit so many points is essentially what established QCD as the theory of the strong interaction, the fact that it works. And it also allows you not only to, measure the shapes of these parton distributions, you can also put the value of the strong interaction coupling into your fit and give you measurements of the value of that interaction coupling. So it's a very powerful technique. Now, what comes out from it? What I'm showing you here are parton distributions now in a bit more detail than we saw before. And what we've got across the top are U valence, D valence, and gluon. And in the middle, the anti-U quark, anti-D quark, and anti-strange quark. They're plotted on a log scale in X, and they're plotted for the results of 3 different groups, all of which do their own parton fits with slightly differing choices, as I indicated on the previous slide. And when you look at that at first sight, at least, you'd say, at least I hope you would say, it's working pretty well. People are making really quite different choices, and what they're getting out is very similar looking parton distributions. Right? So, that just looked at only overall distributions, it looks quite good. Some things are clearly better known than others. Things like the gluon and the strange quark are the least well known. So on this scale, it looks fine, but what if what we did instead was take ratios, say, of two of the parton distributions, let's say the CT1 in blue and the MSHT in red, to that of the neural net determination in green, and look at it in ratio, and you'll see that what you saw on the slide above, once you look at it in ratio, doesn't look anything like as good. There are discrepancies going on there of, well, if you really go down to very low X, of more than 30%. And how bad the discrepancies are depend upon the particular flavor of quark or gluon you're looking at. In particular, you would note that the discrepancies tend to be worse up at the high momentum fractions, high X, and again at the lower momentum fractions. They can be reasonably good in the middle. Now, I think this is all to emphasize that the standard model is nearly not as well known as you might think. The reason it's not well known is precisely because of the QCD sector, the strong interaction sector, where our lack of knowledge of parton distribution functions limits our lack of knowledge of all possible cross-sections that you can get out of that. And I repeat again here the formula I gave for a cross-section of a production of a particular process at the LHC in terms of the parton distributions of the two protons that are going into that. And the kinematic plane I've put up here for the 13 TeV collisions we've been looking at so far shows you the region of the lepton-proton experiments, HERA, and some earlier fixed target in the green in the bottom right corner. And we're now taking what we've learnt from them and evolving it, let me just get a pointer on that. We're evolving it up in Q squared, right, from where we measured it in the lepton-proton processes into now this proton-proton process using this master equation to calculate all our cross-sections. So one way it's useful to look at the uncertainties on parton distributions at the LHC is in terms of what are called parton-parton luminosities. And what that really means is that you take this master equation and you look at just the bits in this equation, which are to do with the partons themselves and not to do with the actual cross-section you're looking at. So what I'm calling a quark anti-quark luminosity here, right, is a convolution of Q from one proton and Q bar from the other and vice versa. And we evaluate that right across the kind of scales which are probed at the LHC, where the scale on the axis here, M sub X, right, is the overall mass, center of mass energy of the total final state X, which I called X in the slide above. So essentially, when you do this convolution, a small scale mx comes from the small parton, fractional parton momentum x in the PDFs, and a large scale mx corresponds to such large scales. So you can see more clearly here in the QQ bar luminosity plot the fact that uncertainties are greater at low scales and at high scales. Now, again, I should note that this parton luminosity is shown as a ratio to that of the neural net determination to illustrate, how well we do or do not know these. So this quark anti-quark on top and gluon on the bottom, right, for the luminosities. And if you're trying to produce something like a W or a Z boson, the scale you're trying to produce it at is 80 or 90 GeV. So that would be somewhere around here. Well, things aren't too bad. For the Higgs at 125, it's really not too bad. But if you're trying to go up to regions where you might be looking for new physics at, several TeV, our parton distributions are getting quite badly known. Now, why does this matter, right? So, just one example that has been measured so far. This is a 13T at 13 TeV. It's a spectrum of the Drell-Yan production. That's production from Q in one proton and Q bar in the other, making lepton plus, lepton minus. This is what we're actually measuring. And here is the cross-section for it as a function of the invariant mass of the dimuon system. And roughly where the data is running out, around 2 TeV, you can see some predictions for possible beyond standard model physics here, like a higher mass Z called a Z prime would make a bump like this, or a contact interaction at 20 TeV would make a change in shape like this. And what you can see is it's going to be hard to tell this from the background if the size of the uncertainty of our measurement, due to our lack of knowledge of the parton distribution functions, is as large as it currently is. Right? That's why this really matters. It's impinging on our ability to make discovery physics. So that's an example from the high XC QQ bar. There's also very interesting to look at processes which might be initiated by gluon, as for example to supersymmetric particles like gluino. And if we exaggerate the uncertainty in the gluon luminosity plot up at high scale, this is just a linear scale now to show uncertainty at high scale, that unfortunately transfers into a gluino pair production uncertainty that is very large in the present day. Now, also thinking about the Higgs itself. In fact, gluon is a dominant channel for the production of the Higgs boson. We've written here there are 4 possible channels which are listed in this table, and the uncertainty on them is partly to do with our predictions at the relevant scales at which we should be making predictions in red, and partly to do with parton distributions in blue. And the uncertainty on our parton distributions is a major contributor to our lack of, being able to exactly predict what the Higgs cross-section should be. And if you can't predict it exactly, you can't say exactly whether what you're seeing is a standard model Higgs, or there is room for, in fact, there being beyond standard model physics in the Higgs sector. And very interesting at the moment, actually, as well as limiting our ability to identify beyond standard model effects at high scale, which is what we really thought we'd be looking for at the LHC, it now turns out that uncertainties on the parton distributions are also limiting indirect ways of looking for new physics, which you might hope to make by measuring discrepancies from standard model values. We think we know how to calculate something like the W math, right, which is calculated in terms of other standard model parameters like the fine structure constant and the weak coupling constant, but it has in it a term which represents loop diagrams that I'm showing various examples of here. And the loops contain, presently known particles like the top quark for Higgs and so on, but would also contain beyond standard model particles if such things exist. And what that would do would increase the value of the mass of the W you were predicting from the standard model value. Now, it so happens that just recently this year, Fermilab came out, well, the CDF experiment came out with a measurement of the mass W that is indeed, there it is, rather higher than the standard model value, where all the previous measurements have not had sufficient accuracy to really say that. And this is an astounding claim they're making, right? It's about 7 deviations from the standard model value. And that really could be an indication that we are seeing new physics in this deviation. But we never believe just one thing. It has to be checked. It can be checked at the LHC, but the most accurate LHC measurement to date is from Atlas, and that's shown also on the plot here, right? And its overall uncertainty of 19 MeV is about 10 MeV worth of that is coming from the Proton distribution uncertainty. And it's going to be hard to actually improve that, right? The LHC uses PP rather than PP bar, and its kinematic reach is different from that they had in Fermilab Tevatron. So the PDF uncertainties we have to contend with are at somewhat lower X, and they're essentially in C quark to C quark, not valence to valence. So this is a difficult job that we have in front of us, and we really need to improve our knowledge of Proton distributions. Now, I'm just looking at my watch, so I think I'll skip this extra example on sine squared theta W in the interests of time. It's a similar argument, but there hasn't been any discrepant measurement of the weak mixing angle. And I'll move straight on to how is it, in fact, we're hoping to improve matters. So we are, in fact, now using many other processes than just the deep inelastic scattering for the determination of Proton distributions. We're using data from the Tevatron experiments, like that Drell-Yan data that I mentioned earlier, and from the LHC itself. We're using the rapidity spectra of the W and the Z, for example. We're using jet PT spectra. We're using top anti-top cross sections. We're using bosons plus jets and bosons plus heavy flavors. We've extended the previous kinematic region we had with HERA up here with LHC data. A great deal of this is the jets, but you can see the Ws and Zs and the tops and so on it as well. There's one danger with doing this, and that is that if you really are putting all this high scale data in your fit, and some of that high scale data might have the beginnings of new physics in it, you're kind of fitting it away into the Proton distribution, but we will come to that. Let's see how much the LHC data has been able to improve PDFs. So this is an illustration from the neural net group comparing their PDFs in ratio for their best determination in green to what it would be without LHC data in pink. And this is for the U quarks, D quarks, charm and gluon, right? And you can see, looking at that if you look at the size of the uncertainties, they certainly have improved. Also, in some cases, the shape has changed. And unfortunately, the kind of data that they've put into this, they're already very good data from the LHC. Some of the W and Z production has uncertainties as good as order of 1%. This is not really likely to get better because it's not limited by statistics of what we've been looking at the LHC so far. It's limited by experimental systematics. Another remark I'd like to make on this is just one group set of determinations, and they made some specific choices about which sort of data they were putting in, which top quick differential distributions, which jet data, and so on, which would not necessarily be the same as with other groups. So to know what the overall uncertainties are, we have to look at all of the PDFs. I have a sort of by the by here because of Aurora's interest, but these curves have recently been improved by a new determination which has very small uncertainties, but not all groups accept this yet. So let's look at what all groups are doing. If we look here, the top two plots are about uncertainties, and they're showing you the three groups, the neural net people, MMHT, and the CT group from the previous generation of PDFs, and the combination that was called PDF for LHC15, which was made of these in the red. And now we look over this side and we see the more recent determinations from CT, MSHT, and neural nets, and the new overall determination. And you can see when you look at uncertainties alone that everybody's uncertainties have decreased a bit. This is great, right? But At the same time, if we look at something like the gluon-gluon luminosity, what you'll actually see is there was a greater concordance about the gluon luminosity around the mass of the Higgs here in the previous generation than in the modern generation. So although the uncertainties have decreased, the divergence of the central values has also increased. So this means overall, you don't necessarily get better agreement as time goes on. And the PDF for LHC group has made a recent combination of the three PDFs. If we just look at, these are plots of LHC cross sections against each other, like W minus against W plus against Higgs, and so on. And they're ellipses of predictions from various PDFs. If we just look at the orange one, which was the previous PDF for LHC, and the purple one, which is the new PDF for LHC, in each plot, you will see that uncertainties have overall decreased for LHC cross sections. But unfortunately, it's not an improvement that would really be enough to reduce the PDF uncertainty on something like the measurement of mass W by any greatly significant amount. Now, we are, of course, we've got a new run of the LHC going. We're going to have a high luminosity run, we think. And there has been a study of potential improvements in the Proton distributions from what we'll get at the high luminosity LHC. And the way this was done was to make pseudo data for various processes, assuming a high luminosity. And what was put into this was processes like top quark pair production, W plus charm, high mass Drell-Yan, and so on, concentrating mostly on processes which still are statistics limited, so that an improvement in statistics would help, and making some reasonably realistic assumptions about systematic uncertainties based on experience with real data. So there were assumptions as to what the possible reductions in uncertainty of systematics could be, and indeed about what the effect of correlations in systematics could be. So, when you're making this kind of pseudo data guesswork, this is about as good as you can do, but you shouldn't forget it's a somewhat ideal situation. And what it said was that compared to the previous PDF for LHC, the high luminosity LHC, with a couple of different scenarios, A and C, about how good the systematics would be, could give you a pretty, substantial improvement in the gluon, gluon, D-quark, strange, and U-bar uncertainty, maybe up to a factor of 2. But as I think I've already said, I think that's slightly a bit optimistic. And one of the reasons that I think it's optimistic is that realistically, LHC data involves combining many different data sets, which are actually analysed by different groups at the LHC with differing procedures for the evaluation of systematic uncertainties. And that makes cross-correlating them rather difficult. And such correlations are not usually known or applied. So recently in Atlas, we did some work where we used various types of our own LHC data, and we evaluated the largest correlations that affect the JET data sets. And we show you here, just in terms of D-valence, D-bar, and gluon, what the difference is between accounting for experimental correlations in the red or not doing so in the blue. Now, it's not enormous, but if what you're claiming is that you want a 1% accuracy on Proton distributions, then unfortunately it can at times get rather large. Another issue is that the current state of the art of extraction is at next to leading order in QCD. In fact, there has been a very recent one by the MSHT group at N3LO, but it's still approximate at the moment. The usual way of evaluating what the uncertainties might be if we could go to higher order of the calculation is to make a change in the assumed scale. So say for something like W and Z production, the usual assumption is that the scale of the process that you're looking at is the mass of the W or the Z boson. but it doesn't have to be. It should be related to it, but it doesn't have to be exactly that. And generally, you can assume that you could vary it by a factor of 2 up and down, and look at whether the parton distributions depend upon the scale assumptions. And again, to some extent, they do. And the other thing I mentioned was that there's a danger when you're fitting high scale data like high PT jet data that you might be putting into a parton fit to the standard model the very beyond standard model effects that you'd like to look for in deviations from your predictions. So another thing we did was cut out all the high scale data from our fit and reevaluate our parton distributions. Now, this is all done on a linear X scale here to emphasize the differences. There are differences. They're not enormous, particularly when you consider on all other plots that I've shown you. I'm sorry, that went the wrong way. Yeah, on all the other plots I've shown you, what I'm looking at in the plot on the current page is all crammed up here at very high X. So it's not as perhaps as strong as it looks, but it's something we have to worry about. Now, how could we actually do better? I would suggest that we could do better with new deep inelastic scattering machines rather than with proton-proton machines. And this is just the final part of the talk to say that there have been suggestions about future deep inelastic scattering machines. There's the LHEC project, which suggests putting an electron LINOC into the LHC proton beams. There's an electron hadron option at what's called the Future Circular Collider project, also at CERN. But there's also in the US the electron ion collider, which will be at Brookhaven. And if we look at the kinematic reach of each of these, where we have been with HERA was here in the orange. The LHEC would come, it's mostly further down in X, and the FCC hadron electron option even further, whereas the EIC goes the other way and pushes up to higher X. So these are lepton-proton DIS machines where I think we could get an improvement at both ends of the spectrum, low and high X, if we could ever get to build them. The LHEC, I mean, I already said one of the issues with LHC data is it involves the combination of many data sets analyzed by different groups. But if you had something like an LHEC or indeed the EIC, that's not the way the experiment's done. You consider the whole kinematic plane all at once, so you get a very consistent data set across X and Q squared. And that could represent a tremendous potential for the increase in the precision of parton distributions. And I won't in this talk mention that it also accesses a rather interesting region at low X. And this is just to illustrate the sensitivity to the gluon and the C at low X, where we have a level of uncertainty at low X now in the gluon, which could be taken down from present levels here to this blue curve with the LHEC. That's for the gluon and that's for the C. And then if we consider the EIC, the impact has been also assessed, and it's going essentially from where we are now in the blue down to the red at high X. So a considerable improvement. So just to summarize what I've been saying, what have we in fact learned about the deep structure of the proton in the last 40 years? We've learned it's full of partons, quarks, antiquarks, and gluons. And the harder you look, literally, the harder scale you go to, the harder you look, the more of them you see. This has established QCD as the strong interaction and measured its essential parameters, both the parton distributions and the strong coupling parameter, and set the background for discovery physics at the LHC. But the uncertainties need to be further reduced, and precision parton distributions are definitely needed to reduce the background in searches for beyond standard model. And they're also needed for these precision measurements of standard model parameters, where it's the small deviations from the standard model values that could tell you that you've actually got new physics. The measurements at the LHC will improve our knowledge, but dedicated deep inelastic scattering machines can do better, and the EIC at least is definitely going to happen. So I think I'll stop there, okay?
Thank you so much, Mandy, for the talk. Thank you. So do we have questions? Please raise your hand if you have questions. Let's see if some of the students want to ask something. So let me just ask one, why are people just, oh, I see one. Leon, please.
Can you comment what's the impact of the uncertainties of the PDFs on the determination of the weak mixing angle?
Aurora, could you repeat the question to me? I didn't quite catch it.
You had a slide on the weak mixing angle.
Oh, yes.
So can you comment on the...
Yes, the thing is that, okay, this slide is simply to say that the uncertainties as we have on the weak mixing angle today would, the statistical component that's in black would go down in time, obviously, right? But actually the Proton distribution uncertainty in the blue would not necessarily decrease at all unless something is done. And this was an illustration of an idea had by CMS that they could try to improve the NNPDF partons with the input of the very same data set from which they're looking at the electroweak mixing angle could be input to try to improve the parton distributions, and that would lead to some decrease in uncertainty, as is shown in the red. But this is really just an illustration that the weak mixing angle is another parameter predicted rather very precisely by the standard model, but which depends upon parton distributions. And so if you really want to, think that you're seeing new physics in deviations from the standard value, you need to improve your PDF uncertainties.
Okay, thank you. Do we have more questions? Let's see. Okay, so you tell me that there are no more questions on YouTube. So Mandy, thank you so much. I have a few questions. So perhaps for the students here, there are many students in the audience who would like to understand the impact on PDF, on the parton distributions, on the proton physics for the BSM. Do they have a takeaway message for them? Because most of them don't really, many of them work on BSM, but sometimes they don't really know what would be the impact of QCD. So if you would have like one sentence, one key takeaway message for them.
My takeaway message would be, if you're trying to evaluate uncertainties on a BSM process, and you want to get some idea what are the current level of the uncertainties, I think I would definitely use the PDF for LHC combination to make a fairly conservative estimate of what my uncertainties are. I wouldn't take just one group's word for it. I'd try to take our best effort at the combination.
Okay, thank you. Dana?
Yeah, I have a question. The resultant cross-section of the parton collision gives us a new particle or what? My question is from the collision slide in the beginning of the conference.
I think she refers to the first plot you show with the 14 TV proton collision.
Sorry, can you say that again? What's the issue?
I think there's a question about the first plot you showed in the second slide about proton, and then you add proton, the hard cross section, and what the X. Capital on the first slides. Yeah, this one here. Yes. Okay.
Well, also I think I had it on
at the beginning of the talk.
Yes, this one.
Yes.
Yeah, I mean, it's just that in principle, a parton and the parton and parton can make anything, and this X could be beyond standard model, or it could just be something completely already known. But whatever it is, our actual cross-section for producing it depends not just on this beyond standard model cross-section itself, but on the convolution with the Proton distributions that are coming together to make it. So we can't get at that, we can't get at this cross-section on its own. In a proton-proton collider, we can only get at this entire process. So to know about this, we've unfortunately already got to know about this and this, and that's the problem. Does that make sense?
So there's not a new particle. It's whatever it can be.
Yeah, but by X I meant anything. It could be a well-known W boson, it could be a Higgs, it could be, you know, it doesn't even have to be a single particle. It could be an exchange, I don't know, an exchange photon to mu plus mu minus, like a Drell-Yan process. It's just whatever happens at the end.
Oh, okay. Okay, I got it. Thanks.
Okay, do we have more questions before I ask a few more perhaps? Let's see if more students have questions. Juan Camilo?
Yeah, I don't know, but you showed a slide with some functions, F1, F2, and F3. Are these functions related, or are they similar to these functions that appear in coherent elastic scattering for neutrinos, or no?
Let me just get. You're referring to this. Sorry, to this slide.
Yeah,
Yes.
for example. Yeah.
Yeah. The thing is that, as I said, I kind of can't teach a whole course in an hour. But if you have this simple diagram going by neutrino coming in, and it's a W boson, then the Lorentz structure of the final state contains a non-zero value of this F3, which doesn't exist if it happens to be a charged lepton that's doing the scattering, but it does exist for a neutrino. And if you try and just look at this part of the sub-process where all you've got is the neutrinos and the quarks, that's actually completely calculable, right, as a fermion anti-fermion process, and you can figure out what the structure of it should be. So I wrote a textbook about this some years ago. Maybe that's the place to look.
Maybe a last question. Isn't this F3 function equal to 0 for isoscalar nucleons or something like that? Even for neutrinos?
No, they're different for iso. I mean, okay, I said, see, it's this weighted sum of quark and antiquark, which if what you've got is just a proton, those are just the squares. But if what you've got is an average of proton and neutron, you've got an average of 4/9 U in the proton and 1/9 U in the neutron, because a U in the neutron is like a D in the proton and so on. And that the average of 4/9 and 1/9 by 2 is 5/18 and so on. It's a so the isoscalar answer is certainly not 0. It's just different from the proton answer. Again, actually, the same textbook where I talk about the neutrinos also talks about this, if you want to really go back to the beginning.
Juan Camilo, I think what you were looking for is elastic scattering, so there will be perhaps form factors.
The elastic scattering.
Yeah, so, and the notation is the same. It looks the same, and it confuses most of the students. Okay.
Yeah, the thing is that what elastic scattering is when this scatter is from the whole proton coherent, but that only happens when the energy of the process is such that this wavelength of this exchange boson is of a similar size to the whole proton system, whereas we're coming at such high energies that it's much, much smaller than the proton system. It's the size of the quarks within the proton. So what we see is point-like structures inside the proton, not the whole proton form factor.
Thank you.
Yeah, I see. It was a confusion between form factors and structure functions. Yeah,
It's a common one.
They
Yeah.
are different things, yes.
yeah, thank you.
Brenda?
Hi, maybe my question is really basic, but I am new in this thing of particles. I would like to know if the quarks, if the protons have, every proton that exists in nature has a different configuration of quarks, and if so, on what does that depend?
They all have a net residue of quark over antiquark of 2u quarks and a down quark. That's what makes them protons. But what they actually have in terms of all these other C quarks and gluons is actually not something independent of us as observers. We as the observer can only see it by firing something at it. And what we see depends upon the energy of what we fire in. So I don't know, if you like, it's possibly an example of quantum mechanics, the uncertainty principle. You can't say what a proton is without the observer interfering with it. And hence, I mean, what you see depends upon what you're doing to see it.
Okay, excellent. Thank you.
Thank you so
I
much.
now understand.
Do we have more questions for the speaker? Okay. Okay, so I think we had a good session of questions. So
Yeah.
perhaps we should just stop the any more questions? No, okay. So thank you so much, Mandy. I think we already had a good session of questions.
Thank you.
Thank you so much for replying to the questions too.
I'll stop sharing my screen then. And,
Okay.
okay, well, thank you.
We don't have questions on YouTube, right? Abril? No hay preguntas en YouTube, ¿verdad? Okay, no. Tell me that no.
Okay.
Okay.
well,
Thank you so
okay,
much
thank you then.
for giving this the colloquium, Mandy.
Okay.